Okay, this is section 2.5, and we want to introduce this idea of non-singular matrices. So, of course, if there are non-singular matrices, there must be singular matrices. But we'll start with our definition here. And a matrix A, which is n by n, is non-singular. Okay, so non-singular or invertible. Okay, so if there exists a backwards uppercase E, so if there exists a matrix B, which of course is also n by n is a matrix that's a square matrix. So when we say n by n, we're just saying it's a square matrix, such that if we take AB, we get the identity matrix. But also, if we take B times A, we get the identity matrix. So if A has a matrix like that associated with it, then it is called invertible or non-singular. Okay. So if any matrix B with this property, okay, is called an inverse of A. Okay, so now notice they're doing something here. They're saying any matrix an inverse of A. So we don't know that in matrices that this multiplicative inverse is unique. But that's the first theorem they do. So they do a theorem 2.5.1 where they say if A has inverses B and C, then B equals C. Okay, so they're saying it's unique. Okay, the inverse is unique. And so the proof of this, usually with uniqueness, or often with uniqueness, I don't know about usually, but often, what we do is we say, well, let's let B and C be inverses. We go ahead and take two things that we say satisfy the property. So, okay, B and C are inverses of A. And, well, so that means if B is an inverse, then we can take B times A and get I. We can also do it as A times B, either one. And similarly, and I think I meant to write it as AB and then BA, but it doesn't really matter. I can move them anytime I want. And so similarly, so we'll say and C times A is I, but that's the same thing as A times C. Okay, so that's just, we're just saying, well, if they are inverses, then they have these properties, because that's by definition. Okay, and so then they say, okay, well, let's take B times A times C. But you see, that's B times I, which is B. And on the other hand, though, if we take that same B times A times C, but we associate it this way, so BA first, which we can do, that's just matrices are associative, then that's I times C, and we get C. But then, but those two things are equal. So, one could write this some different ways. So for instance, if I wanted to clean the, and so see here we can say hence B equals C, something like that. But if I wanted to clean that up a little bit, what I could do, I suppose, is kind of backtrack this way. So I could say, well, look, B is equal to B times I, right? But I could write I as AC. And then I could reassociate here and get my B times A, which is I times C, which is C. And there I've got a nice string of equalities all the way from B to C saying they're equal. So that's a really nice way to kind of clean up what I did up there. So there's our proof that they're unique. And so now, if B times A equals A times B equals I, then we can write A inverse. Okay, so not A to the -1, but A inverse, so that's the inverse one. We don't have fractions with matrices anyway, so A inverse is B. But now similarly, right, you could, you can also say B inverse is A. Right? Either way, if B is A inverse, then A is B inverse. Okay, so then another way to say that then is that the inverse of A inverse is A. Okay, so let's see. So I'm trying to think, do we want to write any more here? I think we do. Let's see. Yeah. Let's write one more theorem. So our theorem is that if, and this is what, theorem 2, so let me write down what theorem that is. Theorem 2.5.2, if A and B are n by n and non-singular, okay, so that what this is saying is they're both the same size, then their inverses exist, and in particular what we have is that AB inverse is equal to B inverse A inverse. And we can check that by simply multiplying by that. So if I take AB, and so here's our proof. If I take AB and multiply that by B inverse A inverse, right, reassociate, so I get A, B, B inverse, A inverse, then that's AI, A inverse, and I can associate it that way, I guess, and then that's A inverse, which is I. So it worked on that side, and we need to check that it works on the other side, so B inverse A inverse times AB equals, well, same thing, we reassociate and we get our B inverse I B, but then that's just B inverse B, and that's I. So we get the identity either way, and so that's a nice theorem in that if I have a product AB and I want its inverse because I know A and B are non-singular, then I can always compute its inverse if I know the other ones, each one separately, its inverse. And now, so this is all the non-singular stuff. A matrix is singular if it is not non-singular. How about that? Okay, but what that would say is a singular matrix does not have an inverse. Okay, oops, and inverse. There we go. Okay, and I think that's enough for introducing the beginning of 2.5. We have this idea of non-singular and invertible matrices, and we've got a couple properties. Okay, so we'll call that done.